Okay, so let's wait for 2 minutes, then we will start it. Let's see how many else joins. Yeah, hello, am I audible?
Is audible.
Yeah, okay, so we will wait for 1 or 2 minutes more, then we will start the session.
Okay, sir.
Okay, so let's begin. Yeah, so hello everyone, my name is Raja Mukherjee and I'll be taking this tutorial for NPTEL course on reinforcement learning. I'm a research scholar at the Department of Computer Science and Engineering, IIT Kharagpur. For this, so we'll be discussing some tutorials like as we have done previous sessions. So mainly we will be solving problems which were related to week 5. I also will be giving a brief introduction of what was taught in week 5 as well as some coding examples to help you get you familiarized with the concepts. Uh, so so let's begin. Okay, so let's not waste more time. This session is being recorded, so you will be able to review this in YouTube and all. Okay, so let's begin. So week 5. So let me just start off what was done in week 5. So the first concept that was introduced. So in the previous week we came across the concepts of MDP and Markov decision problem, optimal value, optimal value for state value function, everything we have action value function. So those things we have covered. So this week first topic which we start with policy evaluation. So what do you mean by policy evaluation? So you have discovered, you have taken, you have, let's say, found out that you have discovered a new policy pi to solve a certain problem. Okay, so you want to find out what is the optimal value of pi. So how good is this pi? So what you will do is for all state s, you will compute v pi is, right? Now uh, like you want to improve in this policy, you want to improve this policy. Okay, so let me share a graph. Okay, suppose this is your approx value and these are your states. Suppose this is your value function for pi 1. Suppose this is your first function you have derived, first value function you have derived. So suppose this is your v pi 1. Suppose this is v pi 1, or let's say let me term it as v1. Okay, so let us call it as v1. That you have got a value function for this policy pi as v1. Okay, now you want to so you also were given the concept in last week that how can you compare two policies. So you have been given a policy, let's say pi 1 and pi 2, how will you compare it? So the concept was that you will check that v of pi 1 for any state is greater than v of pi 2 for any state s, for all state, for all s belong to capital S, right? So this is the concept of your comparing two policies, right? Now what I am saying that you have selected a random policy pi 1, okay, and the function and the value function, let's say, is v1. So what you want to do is want to improve this policy. Okay, so what is the formula for your policy? So what is the formula for your policy for your value function? v1 is equals to, let's say, v1 at state is v1 at state is given by summation of a pi a by s summation r comma s dash p of s dash comma r by s dash comma r by s comma a, and then you have your r plus gamma v1 s dash, right? This is you have. So last week you have gone through these various Banach fixed point theorem and everything. So the update rule, so we want to update this value function for pi 2. For pi 2 we want to update this function. So what you will do is you will just simply replace this as this. v2s is equals to this, and you will do it for all the s, right? So basically what I mean, you will say vk plus 1 is basically this. So if to understand it more clearly, I can write it as that. So suppose this is your value function for each state s. So this is your value function for each state at value function k. So value function k plus 1 your will be value function at k plus 1 will be a combination of next states in previous, in say previous state, in previous iteration, right? So this equation when you replace use it as a increment as an update rule, when you use it as an update rule, it basically simplifies to this, right? This is your what they say is your policy evaluation. So you will evaluate, and so so in the next iteration you will get a policy which will be better than this. Then you will again evaluate, you will find a policy better than this. uh, you will find a policy better than this, and then again you will evaluate, you will find a policy better than this. And how long you will continue? You will continue as long as there is a change in states. There is a change in states, right? What do you mean by change in states? You will continue this process as long as there is a change in state. So what do you mean by change in states? Change in states is means that suppose you have got vk and vk plus 1 at kth iteration and at k plus 1th iteration, right? Now what does the statement means that there is no change? So when there will be no change, a no change means is that suppose you have a policy vk and policy vk plus 1, at each state there is no change, you are selecting the same actions and getting the same value. The action doesn't change for each value state, the action doesn't change. Previously the action was changing, but now there is no change in actions. So that state you are saying that okay, my policy is done, I cannot improve the policy anymore. And which from where we come which comes the term is policy improvement. So specifically to be written, I can write it as like this. Suppose this is your P and V, so you will do policy evaluation to get the V, and then you will use this value that you have got policy improvement to get a new pi. Okay, so from a policy you get a V, and from that V you get a new policy. That is what your this policy iteration does. So a policy iteration process is basically your policy iteration is basically your first policy evaluation and then policy improvement, right? Right. So any doubt regarding these two concepts of policy iteration and policy evaluation and policy improvement? Yeah. So that is what the policy iteration statement does. So basically, now okay. So policy evaluation I have got into depth. Let's get into a little bit more depth in policy evaluation and policy improvement. So how what is your what is your uh, algo says? Algo does is you have a v of s and a pi for each state. Pi of s is basically your action of s. Okay, right. So these things you have. Now for policy evolution you loop delta 0, loop for each s, each state is v equals to uh, so let me just write it in a little improvisation way. So you have v dash v dash is equals to v of s. Next you update the s, summation s dash r p of s dash r given s comma a r plus gamma. What I will write here? So what I will write here? So I will use v dash s, right? The previous one. So let me bring this out outside. Let me write v dash is basically v for each state s belongs to s. Now what I will do? We will find the delta. Delta is basically max of delta comma v of s minus v dash s, right? And we loop until delta is less than equal to theta, right? This is your policy evaluation. This is your policy evaluation criteria, right? So you are we are doing, because at the end of the day your limit uh, k tends to infinity, vk plus 1 is equals to v star, right? So at the end of the day, if you iterate it for too long, like you iterate it for like 1000, 10,000, 20,000 iterations, so at the end of the day it will come very close to your optimal solution, right? So that is what you are doing. So you can define a theta, you can define a theta and say that this is my threshold. If the difference, if the change in the magnitude of my of the policy difference, the value difference is less than that of theta, then that is my optimal result that I want. That is optimal which I can be assured of, right? So that is your policy evaluation. Okay, and how now what how you will improve it? Okay, so again let me write another important uh, thing up, right? So here you have, so suppose you have you have been given v gamma, you have been given v gamma and sorry, you have been given pi, p and gamma. You give it to a dp, you are giving it to a dp, and you are getting the value function, that is your v of pi, that is your policy evaluation. Now if you give p and gamma to the dp, you will get pi, so that is your policy improvement, right? So what we need is what is pi? Pi is the policy. So if you look at this algorithm, so we have pi is the policy, then you have you require this gamma. Okay, gamma you will get, the gamma you will be given, gamma is there, this is the pi given, and the other part that is given is your probability distribution. Okay, so you are using the probability distribution here, transition probability distribution. So that is how that is the thing, that are all the things you require for your policy evaluation. So now once you have evaluated the policy, now what is the thing you need to get? You need to get the, it will to improve the policy improvement slash update. So you will go for each state belong to S, you will take the old action, that is basically your pi of S. Now what you will update pi of S as? Pi of S is you are updating as, so you for a state S you have got a pi of S, means you have got a set of actions. Okay, so you have previously selected, so which action will you choose? So you are state is and you have few actions given, so which one you will choose? You will always choose the one that gives you the max action. Choose one, choose max, right? So that is only we will do here, we will select the one with max. So we will choose argmax a summation s dash r p r plus gamma v of s. Okay, and if pi of s is not equals to old action, then we will again come back here. Okay, so the motivation is similarly, so the motivation remains the same. So you will check basically this, right, that at any state whether we have improved or not, at any state whether the previous action, suppose I think one thing we can all agree, right? Let me propose this question, and let me see what answer can I get. So this thing you will agree, right? So the value function here and the value function we get after this loop ends are different, right? So this thing you can agree. So the value functions with which you start the process and the value function with which you end the policy evaluation process are different. So this part you agree, right? Yeah, so this part is clear, that we are aggressively like incrementing the value function, so obviously the value function which you started is greater than the is less than the value function which you got, obviously. So one thing is clear, that your policy need to be updated, because you have found out a better policy than the one you previously had, right? The value, you have got a better value than the one you have previously had. So now you need to find out the policy. And how to get the policy? Searching for policy is basically searching for the action at each state. And which action you will choose? Obviously the action that will gives you more value. So so in the policy improvement state, we are basically doing that. We are trying to find out the action which gives me the maximum value, and that's why I am updating my old policy. So this portion does basically nothing except updating the policy, which is what does that? That is basically selecting the maximum, the state which the action that gives arguments. Yeah, correct. The the action that gives you maximum value. That is the simple fundamental. Okay, I guess this. If I'm being honest, like the proof that was given in the class, it was much more tougher than the algorithm this you have. Okay, this is much easier from to understand. Okay, so now I will give you another example, not example, another thing to think about. So okay, so what is this procedure? Let me tell us. So what is this procedure set of procedure called? What the thing which you are doing here? What is that? Zarmax. So what form of algorithm does this fall into? Obviously, it falls into your greedy category, right? So this is a greedy algo, right? So not epsilon greedy. Sorry, not epsilon greedy. This is a complete greedy. Yeah, right. So if you remember the bandit problem, so bandit problem was always something like this, that always you take the one which was giving you the maximum value. You were selecting the bandit which is giving you maximum value. So same concept here. So you are selecting the action which is giving you maximum value. Okay, right, fine, all fine. Okay, so now what you are doing is basically you are oscillating towards your optimal action. You are trying to oscillate to your optimal action. So so this is your v comma pi. So here you will get, so this is your uh, policy improvement, policy evaluation, and then is your policy improvement. So you are calculating the value, then you are again coming back to calculating the uh, pi, that is your policy. Then you are again doing like this, again doing like this, again doing like this, and you are ultimately converging to your v star and pi star. Okay, so your this algorithm basically does this. If this one is not satisfied, if there is a change, then again we will go back, then again we will do the computation, and so it basically oscillates between your like between the top and the bottom, like every time you have to do the two loops, right? So what we try to do, we want to reduce this computation. So we want to get rid of these many computations. So one way to do it is value iteration. So what do we do in value iteration? So instead of this oscillation, we oscillate it less. We oscillate it less. We do not go over all the steps and all. We oscillate few. And obviously the advantage is quite familiar, that you will be have to do less computations. You will have to do less computations. So the theory goes like this. So what you will do is loop delta 0 for each s belonging to s. V is equal to v of s. V of s is max of a pi s dash r p s dash r comma a comma s r plus gamma v s dash. Theta is equal to max of delta comma v minus vs until theta less than 0, and pi of s is equals to arg max a, this thing again here. So what we have changed here? Yeah, it got disconnected, sorry. Yeah, now am I audible? Yeah, okay. Sorry, it got disconnected. Yeah. So what I am saying is that, so uh, now we are dealing with much lesser lesser bound. So here we are doing over all the action value pairs. What you are doing here is, we are only choosing the one which gives us max of this. We are not doing over all. So here what we are doing, we are doing over all. Okay, we are only doing here the one which gives us max of a, right? We are only doing over the one which is giving us the max value, not everyone. So this one is small, so you don't have to accelerate much. So in a way we are combining both the steps here. So we are combining basically this and this together to some extent. So here it was picking up only the argmax, and now we are just choosing the one which gives us the max value, choosing the action that gives us the max value. Okay, so that is your value iteration and everything that was done here. So I will give you an coding example. Okay, so let me share this tab. Okay, so let me connect this. Let's get connected. Okay, fine. Okay, so let's start. Let's import one. Let so we are trying to. So let me give you an overview of what I am trying to achieve here in this code trying to do. So this is called a frozen lake problem. Okay, so suppose. Okay, so suppose you are currently here. You are currently here. Uh, that we is if is if h triple h hffg hffg. Okay, so suppose this is a frozen lake problem. Suppose you are currently here in the you are currently in this position. You are currently in this position and you want to reach here. Okay, now s is your start and g is your end. F refers to this lake frozen, and h refers to hole. So one possible traversal path will be like this, right? So so a man can walk. So you can walk over the frozen part, but you cannot. So if you go by this route, it is okay. It will you won't face any problem. But if you try to go like this, this in this hole, so you will fall down and you will die. So that is your problem, frozen lake problem. So that is basically your frozen lake problem. Okay. So we will try to solve this using our dynamic programming approach. Okay, so the here is your problem state, current problem state. Now here are the actions we have. You can go left, down, right, and up. You can go to the left, right, or down or up for any position, and all positions won't have the same thing because you cannot go to the left or right. That is another problem is there at the corner cases. So let's run this. Okay, so this is your help function. This is nothing. Let's not waste time here. So let's come to this part. This is your policy evaluation function. Okay, so this is your value function. This v is your value function, and we are updating these values. Okay, so this is your say value s. This is your delta, initial delta. Okay, so delta is 0. You see the same thing we have done here, right? The how the code was, how the so this part you remember, this part we are doing it here, you are doing it here. V plus s is equal to action prop into revert plus gamma. right? So that is the thing you are doing here, nothing more. Then you have your uh, delta, you are adding it up, and that is your policy evaluation. Okay, so now let's define the, let's start with a random policy and we evaluate the policy. So this function will call the evaluation. So one more thing, from where should we one start to evaluate the, so from which state should one start evaluating the um, evaluating the function, so evaluating the problem, the policy, from the first state or the last state? So suppose you have been given a value function, right? So you have your value function, you have been given a value function v1, and so let's start this one. Let's tell this. So you have been given a, you have been given this value function pi1, right? Policy pi1 and your value function v pi. Okay, for first instant. So from which state should one start evaluating? Think about it. First or last? Think about it. First or last? Yeah, reverse. Yeah, now you have got it. Because from the reverse one, you can easily build up to the top, right? Right. So reverse one, you have to calculate only one, and once you calculate that, you can calculate the next, because the reverse one will only you will have to calculate, right? So so the so you need to get the so if I am if I am being clear, so you need this first, right? You need the next state value, right, before you can calculate your state value, update your state value. So it is much preferable if you start from the last state and then go to the top. That way you can calculate all the values at one. Okay, so share this tab. So so you if you so you can now here look at how the evaluation starts. So first you are evaluating these two states, then you are evaluating this and this. You see, at the end of the day, by back propagation, every one of the states value will be calculated. So you, let's go to the last at the moment. So this is the final state, and here you have calculated the value for all states of ice. Now you want to get q pi from v pi. Well, what do you mean by q pi from v pi? So basically you want to get the you want to get the policy. You want to get the new policy. Okay, you run it. Okay, now you will want to get the policy improvement. So see, in the policy improvement, you are trying to find the highest one. You are trying to find the highest one. Okay, so now let's plot the policy from a single greedy improvement step, right? So this is only one step. So if you look at this, here is your one way of going from this to this. From this state to this state, you can reach by here. This is your one optimal solution you can getting. This start, and here the goal. That is one optimal space. Similarly, also you see from all the states you have found a solution to go to the goal. Any state, from any state you have got a solution to go to the goal, right? That is one solution you have got. Next, uh, yeah, okay. So that's one value draw and non-value draw. Okay, fine. Now let's use a bigger grid. Okay, so let's plot it. So here you get same kind of policy evolution chart. Now let's solve it, completely solve it. So here it was only one grid step. So we will only show it for one step, right? Now we want to completely solve it. So what you did was you first evaluate and then call the policy improvement, and if there is no change, and then again we will continue, right? That is what we have done here. You see, policy improvement, policy evaluation, policy improvement. We evaluate from the previous policy and the new policy. If it is less than theta, then break that, done, we are done. Else copy the new policy and then again continue. Okay, now we try to run it. So how many iteration did we run? We run it for uh, until and unless it converges. Okay, so until and unless it converges, we have done it. Okay, now here we got, let's see, you have got a new optimal path. So new optimal path is here to here, then here, then here, then here, right? You have got a new optimal path from this to this to this to this to this, right? But previously it was this to this. So you have got a new optimal path which is giving you a more better result, right? So that is how you do the policy iteration, both evaluation and improvement side by side, right? Now let's do the value iteration. So now let's do the value iteration. You see, value iteration, it is same. We are doing the max, not the entire one. We are doing only the taking the action which is giving me max value. Okay, and then we call the policy improvement. Nothing more, nothing fancy. When once this for loop is done, and now let's plot it. Okay, you get this one. So now this gives you a policy, but it says that this is now not the only option you have. You can also go down and go this side and go this. So this is also a way you can do it. So nothing fancy, like it's just cost you much less uh, effort. If previous one was giving you a headache of many computation cycles, this one is giving you a very less cycle computation. Okay, so so if you have given the chance, you can write this code. This is nothing much fancy and all. So the algorithms are itself very simple. Nothing hard to write it down and not do it. Yes, yes, Saran. You can ask what you want to know. Yeah, this is collab only. Yeah, so in the resource folder for part of the my part of that video slides and all, so there you can find this one. Sir, that one is policy improvement or iteration? Which one? This one is value iteration, and this one is your policy iteration. Here is your policy improvement. Yeah, I mean, in this value iteration, you can write a policy improvement only, but because it is same, you are just picking out the last best one, and so basically you are, yeah, I mean, calling it a policy improvement is like, if I can have written it a much something like policy extraction and all, but it's same, nothing more, nothing fancy, anything. Okay, so this was your dynamic problem programming solution. Now let's come back and discuss the other things that were done this week. Uh, Practically speaking, these are much easier algorithm, not hard for. So you are introduced to Monte Carlo methods. Right. So so let's get to this one fast. So in Monte Carlo, so so in DP, what is the problem? Why we should go to Monte Carlo? So if you remember DP, pi, p, and gamma. That gives you value, and p and gamma gives you pi. Right. So the problem is this state transition probability. So this is your state transition probability, and it also, if you have noticed, it also uh, takes in the reward and everything, right? Now consider the situation like, so state is basically your random variable, right? State is basically your random variable, so it is basically a random variable, right? So consider the situation of those dice rolling. Okay, suppose you have been given 12 dice. You roll it 6 times. You roll it 6 times. What are the possible value of sum sum of dice, right? So you're rolling the dice, you are calculating the sum. So you have been given 12 dice, you roll them, and you compute the sum of the top value which is coming. So what is the minimum value and the maximum value? So the minimum value will be 12 and maximum value will be 72, right? So 12 into 1 and 12 into 6, right? So that's a total of 62 values, right? 61 values. That's total of 61 fixed values. Fixed 61 fixed values, or like, let me say states, right? So here number of states will be 61, and this is a very small scenario I am saying. The number of states may explode if you have to maintain the state transition diagram for every one of them, right? It will get chaotic, it will basically get chaotic after some time. So what way to solve this one? So this Monte Carlo methods derive some of your intuition from how you are doing your bandwidth problem, where you are just basically sampling at random, and the one which is giving you the maximum reward, you choose it and continue your task, right? So your so this Monte Carlo method goes quite similar to it. Okay, so So you generate a episode randomly, sample, you calculate the reward return, and then choose the action which is giving you maximum return. Okay, so if I have to write it down formally, your Monte Carlo evaluation, so it will something go like this. So this is your evaluation. So the concept remains same. Pi to the concept remains same. Pi to v is your evaluation, and v to pi is your improvement, right? So evaluation vs return is list for each s, loop generate a episode for pi is 0, a0, r1 is 1, a1, r2 dot dot dot, g is 0, loop for each step of episode, g is equal to gamma g plus r of 1, rt plus 1, append g to return of st, and b of st is basically average return, right? Nothing, we are not solving a big calculation of like dp, like the tabular format. What we are doing is basically we are finding out the reward after at each step, like we sample it. So you basically generate an episode. This part is basically the sampling part, right? At each time if you sample it, so you will get a new uh, your new episode. So you will then loop over it, you will get what the return is getting, and you are averaging it out. Okay, so that is your basically your Monte Carlo evaluation. Now if you want to find out what is the again we come back to this part. So this one is done, so this evaluation is done. Now you have to find out this. How will you find it out? You will at each step basically take, so this one will remain same. At each step what you will do, you will find out the qa pair that gives you maximum return, right? You have to find out the action that gives you maximum return. That is how you find out the pi. I mean it's completely same, but there is one difference, and that difference again you have witnessed in bandit. So what happens in bandit if you follow a greedy algorithm? If you follow a greedy algorithm, what happens in bandit? So you over the time you will not explore anything, right? You are just selecting the same one which is giving you the reward every time, the same reward. You are thinking that okay, this one is giving me better reward every time, so why not I will choose this one only, right? So here you are missing the exploration part, right? Now here they give you the chance to explore. How it give you the chance to explore? There is one simple trick. So this part. So in this part, you your each, instead of selecting uh, like always the same, what you do is you select this with a probability. You select that, suppose action A has a probability of being selected 40 times, so you select it 40 times out of 100. Let's say action C or D has some other probability. You sample it based on that probability, and then you continue the work. Right, that gives you an exploration part. Right, that gives you the exploration part, and that is how you get the Monte Carlo estimation for exploding thing. Right, that is how your Monte Carlo improvement is happening. Now if you don't have, so now another problem happens in this case. Okay, so you consider the frozen lake problem, right? So in the frozen lake problem, uh, let me just draw the show this figure again. So suppose we have this problem. So suppose you are in this square in, let's say KE. So this square bracket you are currently. So while you are exploring, so it is not always possible that this is your first step, right? This is your first step. It is not always possible. So your first step is always the start, and your end step at always the end. So selecting any randomly any point here other than these two doesn't gives you much help. So yeah, it helps you to get a value from it helps you to get a policy to reach from that point to the goal, but obviously it is not always helpful. So what you do is, again you sample it, but in a different way, and that case is epsilon times. So your comes your epsilon greedy kind of algorithm. What was there in epsilon greedy kind of algorithm? That you explore for alpha times and 1 minus alpha time, you choose the greedy one. Oh, same epsilon time you choose the greedy option, and 1 minus epsilon time you explore. Similarly is here, epsilon greedy, yes. So you choose the action, you update the action uh, only epsilon times, and rest epsilon minus 1 times you do not update the item. I'm not writing the whole algorithm again because it will take a lot of time. Okay, so any doubt regarding Monte Carlo and dynamic programming, you can ask. Okay, so let's exploration part once again. Okay, so I have to draw it again. Okay, okay, I will draw it. Don't worry. So you are selecting. So this is the action you are selecting every time, right? Like based on your value function, right? This one you understand, right? Okay. Now, Now let's say, so you have this one of selecting action A, right? You update this probability. So initially each was equiprobable. Initially each action state was equiprobable to sigma, right? So each action was equiprobable initially. Now what we are saying, we will update this value, this probability. So it will be updated to gamma divided by number of action in state S1. Okay, and if A is not equal to A star, else 1 minus gamma plus gamma by A divided by S1 if A is equal to A star. So what does this do basically? So what we are saying is, if A is the argmax, so if A is the argmax, so then we are increasing its probability of selection, right? And if A is not the argmax, we are basically decreasing it, right? This is your exploration part. So next time when you sample, because based on that probability, one which is higher probable will always be selected more, right? So you are doing the exploration in this way. Okay, so let's go to some of the problems. Okay, uh, okay. This one is a little bit bigger, but we will come to this problem at the last. Okay, let's solve the other ones because this will take a lot of time. Okay, so this is the first question. Suppose given q pi sa is greater than v pi s, what can we conclude from this? So you have been given that for any state, for state A, q pi q pi s of A is greater than b pi s. What is b pi s? What is b pi s? So we can write v pi as something or less this, right? Q pi s of A is greater than q pi s comma pi of s, right? This is what we are saying, right? What is this? Your state value function, right? Action value function. Sorry, this is your action value function, right? So what this is saying is that according accordingly we can conclude from here is that A is a better option at state S than pi of S, right? This is what we can conclude from here, right? So that means pi is not optimal, right? That means pi is not optimal. So you can get a more optimal value than pi, better value function than pi. So the correct answer is option C. So any doubt regarding this? Can ask. So let's go to the next one. So in solving an episodic problem, we observe that all trajectories from the start state to the goal state through a particular state exactly twice. So it is saying that you have been given a episodic task, and it's saying it passes to two points, two states. Let's both states are ST. That means it passes through this episode passes through these states exactly twice. In such a scenario, is it preferable to use a fast visit or every visit MC for evaluating the policy? So option is that uh, fast visit MC. Option 2 is every visit MC. Mm, third is every visit MC with exploding starts, neither visit MC. So do you know what is fast visit MC and fast visit MC and every visit MC? So the thing is, you remember we were trying to take the average here, right? You are trying to take the average here, right? Now, now every this one, this fast visit states that for average include all except first. So they had said that for average, take everyone except the first one. First time when you sample, you don't take it. Rest you can use it. Rest of the time you can use it for sampling, for taking the average. Only the first time you miss it, give it a go, give it a miss. Uh, every visit is opposite. Everybody says not opposite, but it goes on one step ahead that no, I am fine with all of them. Will take average for all steps, each steps. So in fast fast visit MC, you take all the states. You don't take all the states. You don't take the first step, but every visit MC you take every state, even the first step include. Okay, so let's. So what is the problem here? Which one will you use? The problem is in the definition itself. So what do you use Monte Carlo? What do you use Monte Carlo for? Is used to solve MDP, right? But all trajectories. But this definition of passing a particular state exactly twice is not correct for an MDP. It doesn't exist for an MDP. For an MDP, each time you pass, each state is traversed only once, at most once, right? So this is the problem. Not applicable for MDP. So option D is correct. There is an issue with the problem statement itself, because you cannot visit for a single episode you cannot visit uh, a state twice in an MDP. That's against the definition of MDP. Okay, so let's go to the next one. Which of the following are advantages of Monte Carlo methods over dynamic programming technique? What are the what are the things of the advantage? So we are able to learn now from actual experience, right? So what you are doing is basically sampling, that is running in the environment. So you are no longer have to deal with storing all the values and doing it, right? So you are going not on time, you are doing on the go, right? So sampling in the environment, so this gives you to learn from actual experience or simulated experience, whatever you want to know, but this gives you a live data, not a not what you are doing in DP where you are storing it in tables and do it, right? So here you're uh, on the live go, like if suppose you have a self-driving car and you want to learn how to you want to car to learn how where to brake and how to brake on a split angle. So you can run it using sampling. You can sample it to a few times and then you will be able to adjust to the braking on a curve. That's what I mean to say. So that can be done in a real environment or simulated environment. So those two are the advantages of Monte Carlo over dynamic programming. Next is the ability to estimate. So the next is the ability to estimate the value of a single state independent of the number of states. Is that an advantage? Is it possible in Monte Carlo just to estimate the value of a single state? Yeah, it is actually possible. There is no hard and strict rule that you have to sample everyone. You can just sample it for one and to find the next state. You don't have to sample it for the whole problem, right? You can sample it for a fixed only one state. So that is one a big advantage, that you can sample it for only few states, one or few states, not all the whole states. So this one is the advantage. Option D, ability to show guaranteed convergence on optimal policy. Again, this is not an advantage because both DP and MC are converges to an optimal policy. Okay, so this is not an advantage. I will say both are thing is equal for both of them. So the correct answer are ABC. Okay, so let's go to the next one. So for a MDP, specific MDP, suppose we have a policy we want to evaluate through the use of an actual experience in the environment alone and using Monte Carlo method. We used to use the decided to use the first visit approach along with the technique of always picking the start state at random from the set of from available set of states. Will this approach ensure the start state at random from available set of states? Will this approach ensure complete evaluation of the action value function or to the policy? So it is saying that first visit approach it is using, and it is picking the start state at random from the available state of states. Will the policy always ensure a complete evaluation of the action value function corresponding to the policy? So the theory is come back to the Monte Carlo is that the frozen length problem I was showing. So suppose you sample this state. This is your start state and this is your goal state. So if you're starting at this option of random available state, so all this state you state about random and then start to calculate the Monte Carlo. So it is not possible that you will always uh, correspond to the like complete evolution will not be possible, because maybe at this state it never reaches the goal state. It never reaches the goal state. Maybe somebody it somewhere gets lost in here or here, right? It may be possible that it is not always able to converge to a goal state. Let's say from any state it goes from there is a dead end. So it is not always possible that it will give you a complete evaluation of the action value function. Okay, so that is the answer. That the answer is no. So this question let's come to. So assuming an MDP, there are n actions, n equals to a, of which each of which is applicable in each state is equals to s, where pi is a soft soft policy for sum. Then which of the following is correct? Then which of the following is correct? So the correct answer is option option D, right? So it will not be option D actually. So when do you choose option D? So this is basically update rule, right? So this option we choose only when we need to update policy, right? Rest of the case it is not always required. So here the correct answer is option C. So your pi star a will always be greater than equal to in alpha by n minus 1. At any point of time, it will always be like this. It will never be less than this. Right. At all the stages, this will be the minimum probability. Okay. So let's come to the first problem which I have left till now. Okay, so this was one of the questions which we tried last week for when we are trying to do the MDP problems. So this is a similar question, but now we will be trying to find out the value, policy iteration and all using the equations that are given. Okay, we will try to solve it. So the question is, you have received the following letter. Dear friend, some time ago, I bought this old house but found it to be haunted by ghostly sardonic laughter. As a result, it is hardly inevitable. There is hope, however, by actual testing, I have found that this haunting is subject to certain laws, obscure but inflammable, and the laughter can be affected by my playing the by my uh, by affected by my playing the organ or burning incense. So these are your actions. So in each minute the laughter occurs or not, it shows no degree. What it will do during the execution time depends in the following one. So whenever there is a laughter, it will continue in the succeeding minutes unless I play the organ, in which case it will stop. But continuing to play the organ doesn't keep the house quiet. I notice, however, that whenever I burn the incense, the house is quiet, and do not play the organ, it remains quiet for a next minute. At the time of writing, the laughter is going on. Please tell me the manipulation of the incense and organ I should make to get a quiet house quiet and to peaceful. So your action states are L and Q. L indicates laughter in the room. Q indicates the room is quiet. These are your states. And there is your action states. These are your 4 action states, where O corresponds to playing the organ and I corresponding to burning the incense. We consider this as a continuing discounted problem, gamma and plus 1 assuming a silent state, and this whole thing, right? Plus 1 on transition to a silent state and minus 1 on transition to a laughing state. Okay. So the question is, what? Uh, suppose your starting policy is pi laughing is equal to silent laughing uh, is equals to incense no organ. So is saying pi L is equals to no organ, and incense, and I, right? So this is your pi L, and that will be your also pi psi quite, right? Also, value at L equals to value at Q equals to 0. Initially, both are 0. What you want to find out is the resulting optimal state action function values for all state action pairs. So basically, it want to basically populate the table where you have your state action values and your state action pairs for all state action pairs. Basically, it wants to find the Q function, Q star A of S. Okay, so these you have to follow the policy iteration, policy improvement plus policy evaluation technique, and as well as value iteration part, and you have to write down all the equations and solve it, nothing more. You have to just write down everything and solve it. So I will be solving partially. Let's say how much I can do it. Rest you can do it after the class. Okay, so let me come here. So first what I need is to draw the reward table and the action table and everything. So what you have currently with you is state, action, next state, reward. So this is your S, A, S dash, R. So you have L. Let me fill this out fast. You have L. So this one I showed you how to do last week. So you can just go and check it. Okay, so let's fill it up. L L L Q Q Q Q Q Q L L L L Q L. Okay, and the transition were like this: plus 1. That means any move to state q is plus 1, so this one will be plus 1, and any move to state L will be minus 1, right? So you got to solve the value function for this. Okay, so let's start. So first, what we will try to do is value policy iteration. So initially you have VL equals to VQ equals to 0, and pi of L is equal to pi of Q is equals to naught and I. Okay, so this part is given in the problem definition. So if you go to the problem definition, you will find that this has been given. This is the initial policy, and initially the value functions are 0. Okay, also given theta is equals to 0.7, delta is equals to delta is equals to 0.7, and gamma is equals to 0.9. So now we will first do the evaluation. So first state, delta is equals to 0. What is value of L? What is value of L? So from L, where we can go? So from L, so current action is also given, right? Value of L. So current action is also given for value policy. The policy, current policy is also given. So current policy is O and I, not O and I. Okay, so let's see what it is there. The value function of L is basically, so according to this policy, so what does this mean? So according to this policy, that the state is next state in this case is this, the current state is this. Did you calculate it? You are writing one. How to calculating it? Yeah, I mean, from the table you can say not say like that. Let me write down the equations and then let's do it. So from L, what are the states you can go? From L you can go to L, or you can go to the state Q. Right? These are the only two states you have. Right? From these two states you can go. Right? So let's write it down. So from PL to L, given policy of pi L, that means reward of L to L pi L plus gamma value of L plus PLQ, that is L to Q transaction pi L, because the policy is pi L here, into R of LQ pi of L plus gamma VQ. Right? So these two definitions like sum it up. So your probability of going from L to L following policy pi L, and your probability of going from L to Q following policy pi L. Right? Now you have to check all of them from the table. So let's go back to the table from L to Q, and our current policy is this. Policy is not P, not O, and I. Right? So let me just figure out these two policies. Not O and I. Not O and I is your this policy. Not O and I. Yeah, sorry, this one is I've written wrong. Uh, this one is not I. Not I. Okay. So these are your two, according to Lee, these are your two policies. Okay. So you can go from L to L or from Q to Q. Okay. Good. L to L on Q to Q. So this will come down to so there is only one action. So L to L, it can go from L to L. So we will definitely pick up this one. L to L, we will pick up this one. Okay. So this will be probability is 1 because there is only one. Then probability of what is the reward? The reward is -1. If I am correct, reward is -1 plus gamma is 0.9 into VL. What is the current value of PL? Is 0. Right? Plus LQ. This part will be entirely 0 because P to L to Q given this policy is not there. So this policy exists from L to L. L to Q there is nothing such transition, so it will be 0. So this will be -1, right? Similarly, let's not waste time and do the other one. uh, to the V of Q. V of Q will also be same, P of Q to L pi Q, R of Q to L pi Q plus gamma value of L, because the next state is L, that's why value of L, plus P of QQ pi Q, R of QQ pi Q plus gamma V of Q, right? So in this case again the first one will be wrong, because first one will be 0, because there is no transition exist between that, and P to Q is the reward is +1. Okay, fine. So the value will be 1 into +1 plus 0.9 into 0, because VQ is 0. So it will be 1.9, right? Sorry, 1 plus 1. So what is the value of delta? Delta uh, is max of 0 V dash Q minus VQ, comma V dash L comma minus VL. It is the max of this part, right? So that will be max of 0. This one is 0 minus 1, 0 minus 1, right? So this will be max of this is mod also, so this part is mod, so it will be 1. So delta value is 1, right? Now the delta value is greater than, so what is the delta value we want? Delta value is given is 0.7. So this one is greater than 0.7, right? So we'll again, so delta is greater than 0.7, so we again evaluate, right? So let's go to the next one. Similarly, now we have delta equals to 1. Now you see we haven't changed the state, right? We haven't updated the policy yet, right? So update the policy, when we will update the policy, when the delta value will become less than 0.7. Until then we will just iteratively evaluate it. We will just iteratively evaluate it. So you will again do the same thing which was done, which we have done before. So that is this part only. So we will write these equations again and do it, right? We will write these again equations again and do it, right? So V of L again will be now what will be? So L to L is 0, L to L part is will be 0, L to Q part will be 0, right? So we only need to focus on L to L, right? So the probability is 1 into what it is, how much was the reward? So reward is -1, okay, reward remains same, -1 plus 0.9. What was the previous value? Now you have to consider the previous value. finally you have to consider the previous value. So that was minus 1, right? In previous case the value we came up for L was minus 1. So we will take this value and substitute it here. Minus 1, so it will be minus 1 minus 0.9 is equal to minus 1.9, right? Similarly, V of Q will be similar, L to Q to L plus Q to Q. Q to L there is no transaction for the current policy, it will be 0. Q to Q will calculate 1 into how much? The reward is plus 1 plus 0.9 into 1, right? Right, so it will be 1.9. So now again we will calculate the delta will be max of 0 mod of v minus v dash, these are all mods, mod of v l v l vq minus v dash q, right? So it will be max of 0. So what was the previous one? Previous one was, current one is minus 1.9, previous one was 1, so that is plus 1. This one is mod comma q of like 1.9 minus 1, right? So this one will come out to be 0.9, right? Okay, so you iteratively solve it until the delta value becomes 0. When the delta value becomes 0, at that time you will update it. Okay, so let me I will so if I try to solve all of this, then I have to sit for another 1 hour. So I will do the trick, and so I will just give you the result. Okay, not the result, but I will show you how to get the policy for one iteration. Okay, so let me show. So let's, after few iterations the delta value will become 0.0561. Okay, in that case the VL value will be minus 4.0951, and VQ value is plus 4.0951. Okay, so obviously we have got an improvement. Now what we have to find out, now we have to use the improvement theorem, right? So what is the current policy? Pi of L is equals to naught of O slash L, right? What is the Q value corresponding to this? What is the Q value corresponding to this? So the corresponding action value is minus 1, right? Minus 1 minus 1, right? And what is the latest we have got? Sorry, let me just, if I have to describe it, let me describe it in a better way. So our goal is to pick the pick action value with max, right? This is what we want to get. So the old action was this. Old action was this, right? Now let's find out the new action. Pi new L. So which A will give me maximum value? Let's come back to here. And which L will give me maximum value? Which action will give me maximum value? You see, these two actions will give me maximum value, right? So this will give me plus 1 plus 1. So these two will give me plus 1, but the current value which we have is minus 0.4951, obviously. So we will select that policy. So we will update the policy accordingly. So we will update the policy as this, one of these two, anyone will suffice. O and I, right? So that is giving me the maximum value, right? So we show, so if we move about all of them, so from L, if you move about all of them, so from L you have got these all transaction, right? From L you have got all these transitions, right? Let me use a separate one. So previously you are following this one. Now what value we got from this is minus 4 point something, right? Now I am saying that out of all the four of these actions that can be taking place from L, we saw that these two will give me more reward. Obviously my greediness in me will always try to pick up, okay, let's pick up this one because this one is giving me better reward than minus 4.3. So obviously we will pick up any of these two and then continue the policy. So the new pi for L will be this. What about pi for Q? Right, so this one is giving me the maximum value and it is anyway greater than any one of them. So if you consider all the transitions from here, so this one is currently giving me plus 4 or something. So based on this I will again still use this value only. So it will be not Q slash not Newton slash what is the policy? Not O slash I. Yeah, so I will continue this. Okay, so in this way you can fill up the whole table, or you can do one thing, you can write the code for this and run it and you will get the answer for this MCQ. Okay, so any doubt regarding this? Yeah, so this one was the last one for today. uh, we will again meet next week. Thank you for joining. Yeah, thank you.